Hey, Dr. Ko, let's talk about a pipe system. So in our pipe system, we have three nodes, and nodes 1 and 2 exit the environment. We know everything of the pipe system: length, K value, diameter of the pipes, the pressures, the Z value, the flow rates. We know the E over D, except for we don't know the height of node 0, the pressures of the internal nodes 1 and 2, and we don't know the K value of the pipe from 1 to the environment. So let's start. First, we're gonna import our NumPy. So we can use this in our calculations. We're gonna name some known variables. So we know that gravity is 9.81. We know the E over D value is equal to 0.001. We know the mu is also equal to 0.001. We know that rho, the density, is equal to 1,000 for water, and we know that pi, we're going to say pi is equal to nt dot pi to make it a little easier on us. So from here, let's try to solve for the head drop. We're going to define a function for the head drop called d head, and we're going to make that q. That's a flow rate. L, that takes into account all of these. K, the diameter and ED. So from here, we're going to say that D is the velocity is equal to the flow rate divided by pi times the diameter squared divided by 4. Now that we have that, we also need the Reynolds number, which is going to be equal to the density times the velocity that we just found times the diameter divided by mu. So now that we have that, we can return our head drop, which will be negative because the big F is negative. It'll be K plus 4 times small f, which is the friction factor, and that will be times L divided by D, divided by capital D, diameter. That will be times the velocity, which we found, raised to the second power divided by 2 divided by g. So we've got our head drop equation. But where do we get f from? So we're going to get f from the Churchill equation, and that takes into account r, or the Reynolds number, and the ED value that we have. So to get that, we have to define a function for the Churchill equation. So we can get the friction factor of each pipe. Like I said, it'll take into account the Reynolds number and the ED value. So let's do that. So now that we have that, let's test it. And we're gonna just put a Reynolds value of 1 in there, and we already know the ED. So that is equal to nearly 16, and that looks pretty correct. So from there, we can now test this. So do D head we're going to say 1 flow rate, 1 for the length, 1 for the K value, 0.1 for the diameter, and we already know the E over D value. So here we get flow rate or change in head of almost -1,000. So let's just say that we have a negative flow rate in there. Let's see what we get. So this number is obviously messed up. So we need to account for any negative flow rates. We're going to do that by taking the absolute value of this, and then we're going to incorporate NumPy sign to apply the sign of the flow rate back to what we're returning. You can see that it fixed our output. From here, we can move on to defining a function for the flow. We're going to call that flow, and we're going to use some new variables. So we're going to say delta head, which will be the delta head, and then we have the length of the pipe again. We have the K value for the pipe. We have the D and the ED, the diameter, and then the ED. So from here, we're gonna, to avoid similar issues with our earlier code, we're gonna say absolute value of delta head is gonna equal NP dot absolute delta head. Okay, perfect. So from here, we're also going to incorporate that if the absolute value of delta head is less than 1 e to the -10th, then we're just going to say that it's 0.0 to avoid any issues. Now we can use the Q guess because we don't know the flow rate for most of them. This will be pi times the diameter squared divided by 4, similar to what we saw earlier, times the square root and this is similar to what we saw for earlier. We're just putting in a guess now. We're going to assume that this is 0.01 based on the Moody diagram that we looked at in class. Now we have the Q guess. Here we can define the function f to 0, and this is going to make our d head equation that we did earlier equal to our delta head equation for the known. So turn d head to L K B E D minus absolute value delta head. Looking at that, we can find our result, and that will be Newton, which will help us find the roots of the function. That'll be f to 0 and q. Yes. That will return dot sign delta head, because we want to still keep in that account like we did earlier, times the result. And these are the functions that will help us find the change in head and the flow rate for our system. Thank you.